We now talk about inductors in an AC circuit. So say you have an AC circuit and there is an inductor and you apply a voltage V to it. So you have the AC sources right here. This is the symbol for AC source, and you have connected a inductor and the applied voltage is V. Now we have read in the previous chapter that there is a self-induced voltage across this inductor. So this self-induced voltage is given as minus L di by dt. So by Kirchhoff's loop rule, you have the voltage applied V, and then you have this back EMF minus L di by dt, and the sum is equal to 0. So this is the sum of voltages applied across the loop. So V minus L di by dt. So you add V to this self-induced EMF, and this is equal to 0. Now V is instantaneous voltage. So this is the instantaneous voltage, and you know that instead of V you can write V is equal to Vm sine of omega t. So this you can plug in, where V of m is, this is the maximum voltage. So V of m is the maximum voltage and V is instantaneous voltage. So we get V of m sine of omega t, this is equal to L di by dt. So we can rearrange this expression. So you multiply both sides by dt and divide both sides by L. This is what we get. Di is equal to Vm by L times sine of omega t dt. Now you can integrate both sides. So integral of di is equal to this Vm and L. So L is a constant of inductance, which we have talked about before. This is just a proportionality constant. So Vm by L comes out. You have integral of sine of omega t dt. Now you integrate it. You know that sine of omega t dt, this is nothing but equal to just this expression. This is equal to minus cos of omega t dt, and that is what we get. You take this minus sign and put it right here. So this minus sign goes right here. So you get minus Vm by omega L cos of omega t. This is equal to Vm by omega L, and you write minus cos of omega t as sine of omega t minus pi by 2. So notice that sine of omega t minus pi by 2 is exactly equal to minus cos of omega t. So now you have the value for current. So we will put this Vm over omega L, we will put this figure as I of m, that is the maximum value of the current. So you have the current as the maximum value of the current times sine of omega t minus pi by 2, and you have voltage right here as V is equal to Vm times sine of omega t. Now you can clearly see you have sine of omega t right here, and you have sine of omega t minus pi by 2 right here. So you can see that current lags behind voltage by 90 degrees. So current is lagging behind voltage by 90 degrees. So this is how we show it in the graph. So say the red is the voltage and blue is the current. So the current is lagging behind voltage by 90 degrees. So this is the maximum value of the current, and we have the maximum value of voltage here. So this is more clear in a phasor diagram. So in the phasor diagram, this red part is the voltage and this blue part is the current. So the current is 90 degrees behind voltage. So this angle is 90 degrees. So the current is 90 degrees behind the voltage. So if this angle is omega t, then this angle here, this is omega t minus pi by 2. So this is how we get the phasor diagram, and obviously you take the projections. So this projection here, so the length of this vector is V of m. So the projection you will get V of m sine of omega t. Similarly, the length of this vector is I of m. So when you project it here, you get I of m sine of omega t minus pi by 2. So now we talk about inductive reactance. So current achieves a maximum value of cos of omega t is equal to plus or minus 1. So that is when this value is equal to plus or minus 1, you get the maximum value of the current. So this portion is I of m. So you take absolute value of this. So you forget about the negative sign here. So this is the, so this portion Vm over omega times L, this is the current. So basically we write I of m as V maximum, that is the maximum voltage, divided by omega times L. So you set this omega times L as x subscript L. So you write Vm over x subscript L. Again, V subscript m is the maximum voltage. And you call this XL as inductive reactance. So the unit is ohms. So XL is called inductive reactance and the unit is ohms. So notice that inductive reactance increases as frequency increases. So notice that as frequency increases, so omega is equal to 2 pi f, where f is the frequency. So as frequency would increase, omega would also increase. Now if omega increases, this XL is equal to omega times L. So if omega increases, XL also increases. Now this is in line with Faraday's law. So if you increase the inductance, then the back EMF will also increase. And this back EMF is precisely what causes the reactance. Now let us see an example. So say you're given an inductor. So inductor has L is equal to 2.5 times 10 to the power of minus 2 Henry. And it is connected to a source of 220 volts and a frequency of 50 Hertz. So the inductive reactance is XL is omega times L. So instead of omega, you put 2 pi f. So this is the formula for omega, where f is the frequency. So instead of omega, we are writing 2 pi f. So frequency is 50 Hertz right here. So you plug in the frequency here, you get 2 pi times 50, and L is given right here, 2.5 times 10 to the power of minus 2. Plug in this. So you get XL as inductive reactance as 7.85 ohms. And RMS current I is equal to voltage over XL. So again, you can see from here. So this also implies that I RMS is equal to V RMS divided by XL. So you achieve from this equation here by dividing both sides by root 2. So you divide left side by root 2. So if you divide this side, this by root 2 and this Vm by root 2, you get I RMS is equal to V RMS over XL. So we are given that the source is 220 volts. We divide by XL, which is 7.85 ohms. So the RMS current you get is 28 ampere. So notice that this is the RMS current and you have to multiply it by root 2 to get maximum current.